Well, with that impressive animation, we arrive at Maxwell's equations, the culmination of our study of electromagnetism. Not that it's complete, but this is a good opportunity to introduce the result of where we've arrived at to date. So Maxwell put together the formulas that we've been investigating so far. Key discovery that he made was displacement currents, where a non-conduction current produces a magnetic field. And he, in a very creative and thorough way, synthesized what was known at the time. So, what do they include? The four equations we've been looking at. First of all, closed integral of E dot dA is Q enclosed over epsilon 0. We know this as Gauss's law for electric fields. Then we have closed integral of B dot dA. B dot dA, and that is 0. Now, it's 0 because this is Gauss's law for magnetism, because there's no magnetic monopoles, or there is no isolated magnetic charges as there are for electric charges. So this is Gauss's law for magnetism. Then we have closed integral of B dot dL, which is mu 0 times the quantity I conduction plus epsilon 0 d phi sub E dt. So it's not just mu 0 I enclosed, but also if there's no actual conduction current, we have a d phi sub E dt as a displacement current in space, like in the region between capacitor plates. So Ampere's law including displacement current, where the change in electric flux acts as a source of B field. And then closed integral of E dot dL, which is minus d phi sub E dt, which is Faraday's law. And a changing magnetic flux induces an E field in the surrounding region. That E field is not conservative. So that is a summary of Maxwell's equations. A couple more comments are in order pertaining to Maxwell's equations. Let's take our region of space, the final frontier, and let's consider an electric field vector in that region of space. Now, the region of space is devoid of substance, although not fields. So it does have fields in there, or potentially has fields. And don't get tripped up with that pun. Now, the electric field vector can consist of the electrostatic E field and the non-electrostatic E field. They're both possible. Considering the electrostatic E field, closed integral of E electrostatic dot dL. Okay, if we multiply E field times length and we go all the way around in a loop or in a closed loop, all right, you should know what that equals. It's 0. It's always 0, which is really saying the potential at point A going all the way around is the potential at point A again. Well, the electrostatic E field is always conservative, is why that happens. It's a conservative force field. So it doesn't take any net work to do that. Now what about the non-electrostatic E field? In this case, if we say the closed integral of E non-electrostatic dot dA, so we're doing a surface integral now, that likewise is 0. Why? Because the non-conservative electric field doesn't contribute to the integral in Gauss's law. Why? Because it's not due to charges. So this non-electrostatic E field has nothing to do with charges. So they're quite different entities here. Now, the conclusion that we can make from this is that the electric fields in Maxwell's equations is the net E field. The equations don't particularly distinguish between the conservative and non-conservative fields, but for the electrostatic E field, if we do a line integral, we always end up with 0. Only the non-electrostatic E field will produce a non-zero line integral. Only the electrostatic E field will produce a non-zero surface integral, because it's due to charges. Okay, well, in empty space, the conduction current is 0. Right? There's no charges flowing. Q enclosed, well, there's no charges in that empty space. It's also 0. Moreover, keep in mind that electric flux, integral of E dot dA. Magnetic flux, integral of B dot dA. And let's specify now, we're talking about empty space, closed integral of B dot dL. Ampere's law. Well, there's no conduction current, so forget that. There's no I enclosed. But this evaluates to epsilon 0, mu 0, d phi sub E dt, but phi sub E is integral of E dot dA, so I'm replacing that here. So we have epsilon 0, mu 0, d dt of integral of E dot dA. And the closed integral of E dot dL, Faraday's law, which is only non-zero for a non-electrostatic E field. It's the d phi sub E dt, and phi sub E is integral of E dot dA, so there it is. Now, what does this mean? Profoundly, what this means is that a time-varying field of either kind, electric or magnetic, induces a field of the opposite kind in the surrounding empty space. And that truly is a profound discovery. And in these expressions, all the basic relations between fields and sources are described. Well, some final thoughts on Maxwell. We have Gauss's law, which derives from Coulomb's law, Ampere's law deriving from the Biot-Savart formulation of currents and B fields. And force from the fields can be summarized as follows. Force is equal to Q times E plus Q V cross B. And these are all the fundamental relations of electromagnetism. If only there were magnetic monopoles, and we'd have closed integral of B dot dA is, instead of 0, M enclosed over mu 0, then there would be greater symmetry and elegance in these equations. But nevertheless, we can't argue with nature. We will go with what nature gives us and simply marvel at the resulting reality that we live in.